Hello everyone, my name is Masood Hassan, Cloud Solution Architect at Google. I'm based out of Toronto. Today I'd like to talk to you about how we have helped a telco customer in Canada to protect their wireless network from malicious activities. In the demo, you'll see a machine learning based network anomaly detection solution where we'll be processing millions of NetFlow log events, and hopefully we'll find some outliers in near real time. There are 4 key areas in the demo, as you see in this architecture diagram. We'll start with number 1, which is where we'll be generating mock data using a Dataflow pipeline. So let's get started. So I'm just going to kick off this Gradle command. So as you can see that we just kicked off a Dataflow pipeline. So let's go to the console and see if it's starting. Okay, so you can see that this Dataflow pipeline has just started. Now let's look at some of the parameters that actually we need to operate this pipeline. So one of them is QPS. Now what it does is it tells Dataflow pipeline to say that, hey, my message rate, the number of messages we wanted to publish is 100,000 messages per second. You should also look into a parameter called topic, which tells that this is the topic information that we'll be using to publish message to. And the most important one is probably the schema location, which is this JSON schema file uploaded in a GCS bucket. So let me quickly use this, pull out our JSON message or the JSON schema file. So you could see the way the schema file works. I take out some of the attributes that's used for the NetFlow log. So for example, source IP, destination IP, similar thing for port, transmission and receive bytes, and the start and end time. And on the right hand side, you see a function, which is based on a JSON, a open source JSON data generator. So the way it works is it's going to randomly choose a username for these attributes. So a lot of those attributes, a lot of those sub functions are actually built in. So for example, username, and then you have an integer function that's automatically randomly going to generate a number between 1000 to 5000. Start time as well based on your current timestamp. So you could see a random function here that's automatically going to choose one of those 3. But there is also, we had to make sure that our data is completely not random. So for example, destination IP, we could use IPv4 function, but we didn't. Because as we are going to group by the destination subnet, we wanted to make sure that we create a custom function called subnet, which is where we limit the number of destination IP within a subnet range. So hopefully that makes sense. So let me just pull out some of the messages. I wanted to see if it's actually publishing right. So I should have a pull command here somewhere. Okay, so you could see that I'm on my pub sub, and I'm using my subscription pool to my subscription ID, and I'm limiting it to 1. So let's see what kind of message it comes out. Let me just do it one more. Okay, so you could see that my subscriber ID and then my source IP, destination IP, it's all random value based on my schema. Let's do one more. So one of the things you noticed in terms of destination IP, it's actually it's not completely random. So it's a subnet start with 12. Okay, and we also have to make sure the end time is always after start time so that we could actually calculate the duration out of it. Now let me go back to the Dataflow pipeline. Hopefully you started publishing some messages. So let's click on right. Yeah, so we already published 13 million records. So this graph is going to start to come up and close to 4 GB of data. Okay, so what I do, I'm going to publish some random messages, which I believe it's going to be an outlier. And I don't know is. Let me just see. Okay, sorry, it's right here. So you can see that my subscriber ID is so it's IMSI number, because in the later part on the demo you'd see that we are going to de-identify the subscriber ID using DLP API. So it's IMSI mobile subscriber identifier, and I have random source IP, destination IP. One of the things to notice here is the transmission byte and the receiving byte. So if you remember from our schema, we actually have a very tight range in terms of transmission and receiving bytes. But for this one, which we believe is going to be an outlier and wanted to see if Dataflow process can pick it up, it's a lot higher. Okay, so let's publish it. I'm just going to publish 2. Okay, so now if you summarize what we have just done here in our architecture diagram, we have a very easy to use Dataflow pipeline that can be used to generate JSON messages in a pub/sub topic with a message rate that we like. And if you look at, one of the things that it's really helpful, because not a lot of the POCs and the projects that we work on wouldn't be able to access customer data, right? Especially if there's a PIA information in it. But with this architecture or with this open source code, we could really generate millions or thousands of messages as we'd like it to be. Okay, so now it brings us to the next step of the process, which is the number 2 you see here. Now, this is where a lot of the, the hardcore stuff is going to happen. So I'm going to explain this very slowly. So we call it the anomaly detection Dataflow pipeline. You could see from the architecture diagram the way it works. So we have multiple sources of data that's coming in to our Dataflow pipeline. So one is pub/sub, which on the step 1 you see where we started to publish those messages. Now I also put some random data on a cloud storage bucket, so that wanted to see that, hey, if we are processing multiple sources. So once the data is coming in, so there are a couple of things actually going to happen. So one is we have to validate if it's a correct JSON message. So just a sanity check to make sure that it's not going to fail. And then we convert it to a data type called row, was Apache Beam row type. And it's important that we do a transformation for a row type, because for the feature extraction portion where we're going to do aggregation of data, it becomes really, really easy to do using this row type. So if you scroll down a little bit, and I'm just going to quickly show. Where did it go? Yeah, okay, so here. So we have a row type, and what we are trying to do is based on the column name for that row, we're grouping by those 2 fields, which is subscriber ID and destination subnet. And it also uses an aggregate field or a function. So for example, for source IP, we wanted to do a proximate count within our fixed window. Similar thing for the source port. You could also see that the different aggregation function that we're using for different fields, right? So for text bytes, we are actually going to do a average, mean, and max. And once you do that, it output the result to this field name. So you could see this is very similar to how a group function with SQL would work. And the alternative way to do this would be to use actually SQL transform. But we wanted to use the Java way of doing things. So, okay, so now that this thing, it has aggregated data and we extracted the features that we need. Actually, before we move into DLP, just want to quickly mention what are the different feature types. So if it wasn't clear from that, the Java statement, what we are doing is max, mean, average for duration. We are also calculating max, mean, average for transmission and receive bytes, a number of unique records, and the approximate count for IP and port. And we're doing this by grouping our subnet and the subscriber ID. So remember the destination's IP that we are getting. So we try to get the subnet from the destination IP, and then we do a group by for every subscriber. So this is where we'd know that, hey, what is our destination traffic pattern would look like. And in addition to that, we are also adding a processing timestamp on our payload. So let's quickly look into how the pipeline would work. Okay, so if you look at the Dataflow pipeline or anomaly detection, so this is how it looks like. It's quite a bit of complex pipeline, but let me just walk you through for each transform. So let's click on, so actually first of all, look at the number of messages currently processing. So if you remember, we are actually ingesting 100,000 messages per second, and it looks like it's actually keeping up. So let me click on this one of those read flow log data. So as I said, it has to process messages from multiple sources. So if you could look at GCS, there's around 101 records. I'm pretty sure for PubSub, look, it's already processed close to 100 million. So we are aggregating, or we're at least getting those messages from multiple sources, and then we are converting or validating if it's a correct JSON message. And once it's done, we're converting it to a row. Then it goes through a fixed window transform. So we are using a fixed window for the demo. I think it was 30 seconds, and the event-based time trigger. And this is why you also look into in here, because all the data that we're reading from GCS, by default, there's no event timestamp, so we actually have to add it. So after fixed transform, let's just minimize this. So after fixed window, then it goes through this feature extraction transform. So let's click on the inside, and it's pretty much what I just showed you before. So now that we have a row type, we're going to aggregate by the destination subnet as well as the subscriber ID, right? So we're adding a columns, we're creating an aggregated row, then we're doing a group by, and then once we have the aggregated data, we're going to merge it. So one thing to notice here, so if you click on feature extraction, you could see that it's actually processing close to 100,000. So we have a 101 million records that being processed, but after extraction the number is actually quite low. I mean, at least half of them. It's because we are doing that aggregation. Okay, so now that you have your source data, we have the aggregation and features extracted. So one of the things that we're going to do next is the DLP transformation. Now, if you remember from our source data, the IMSI, so for our subscriber ID, it may contain the IMSI number. We cannot really store those information to the BigQuery without de-identified. So the way this DLP transformation works, for a Dataflow pipeline, it creates a DLP template. So we are currently using a de-identified template that uses a crypto-based deterministic encryption. And the reason we are using a deterministic encryptions because we wanted to re-identify those data after we store it to BigQuery. Because this is how we would know that, hey, what is the subscriber ID and who we can contact, like what are the other details like email and phone number associated with this information. But we cannot store those information in plain text. Okay, so one of the other things that I should mention in this DLP transformation is, so it calls the DLP APIs in chunks. And the reason it's important, because if you look at, we are actually ingesting 100,000 messages per second, and you don't necessarily want it to call DLP API for every single message. So this is why the chunking or batching of the request is very important for better performance. And that is possible because we are using the stateful processing for Beam. So if you click on, for example, one of those transform, you could see that, so in terms of total number of requests, it's actually 85 million that's going into as a raw record. But when you're batching it, it's the number of records actually quite less. So when you do this, so there's a little bit of challenge is because for DLP, the API request can have maximum 524 kilobyte per payload. So when you're chunking it, you need to make sure that you're not going over it. And the another thing is when you're doing this and calling APIs in parallel, You also need to make sure that you have sufficient quota, or the number of API calls that you could make is actually a lot higher than your default limit, which I believe is 600 per project. Okay, so now that we completed the DLP transformation, so let's go back to our architecture diagram. So we talked about the sources, we talked about the feature extraction, we also talked about how we are processing for unbounded data source, how we are using DLP APIs to de-identify IMSI number. Now that we have done all those three, the last thing, or at least for this part, is to make sure that we're storing all those information in a partition table in BigQuery. So if you look at the amount of volume we are processing right now, so it could be terabyte of data accumulated every day. So let's go to the BigQuery side of things and see how it's looking. Actually, before we go there, so we are using the batch insert. So for the overall architectures, if you look at it, our goal is to find the anomaly as soon as we can. But a lot of those feature extracted data, it may not even have anomaly at this time, or at least we don't know it yet. So we don't want to stream all those information so that it goes to BigQuery, because that will not be the cost efficient way of processing it. So we're doing the batch request or the file load methods from Beam to store the data in BigQuery. So let's go to the BigQuery. Okay, so this is our data set, and sorry, our project, and data set is network logs. So if I click on the cluster model data, that's where all those extracted features have been stored. I click on details, you see that we currently have close to 3.5 billion records, 505 gigabyte. It's a partition table, and we are using the day partition based on the ingestion time. This table is also clustered by destination subnet and subscriber ID. Now, what I'm going to do here, and so if you go back to an architecture diagram, now we are on this third part of our demo. So now that we have all the data on BigQuery, we're going to train those data using a k-means clustering model as part of BigQML. And I wanted to show you how easy this is to train this using just a SQL statement. So let's go back, and I'm going to go to saved queries. And I have saved a query. It's actually a store procedure. So let's just open it up. And okay, so if you look at this, what we're trying to do here, we're choosing, so based on our partition, so we're trying to select a random data set for our train, right? So for example, just for this demo, we're randomly selecting 100,000 records. Then using create or replace model or this statement, and the model type k-means, we're actually going to create a k-means clustering model based on those train data, or so based on those feature extracted data. Now, once we create the model, we're actually not done. Now, the next step would be we need to make sure that we normalize those data. So for every cluster, the points that we have for each cluster, we want it to normalize using standard deviation. So there is series of series of tasks that we need to do now that we have all those information, or all the data. So what I'm going to do is I'm going to run this, and this is you could save it. So it's a multi-statement store procedures. You could literally save it and run it at the end of every day, or schedule using the schedule query that BigQuery has. Okay. So what it means is you're continuously retraining your data and you're normalizing. Okay, so let's keep it running. I'm just going to go to open up another BigQuery. And I want to quickly show the schedule query part. So you could see this normalized data, and I have been running this every day, and it runs and retrain. So when it retrains, it creates this. So first of all, it updates the model, which is our log cluster. Okay, so as you could see that it's completed. It doesn't really take that long. And you could also see how powerful it is just by the SQL statement. We just train those data with the k-means clustering model. So let's click on the log cluster. So it provides you a lot of those. So we know the k-means model, a lot of those model specific data. It's available for us to look at. So you go to training tab, evaluation, and all the schemas. I'm not going to get into too much details on those, but one of the things I wanted to show you is, so look at this normalized centroid data. So now that we have all the data normalized, so for each centroid, we have a normalized distance. Okay. So that takes us to the last part of the demo, which is going to be how we are going to find out if it's outlier or not. Okay, so for outlier. So first of all, when you decided to do how we're going to do outlier, our choice was, either whether it has to be batch versus online prediction. And it's pretty clear that, hey, if we're finding anomaly and we're doing a batch prediction, it may be too late. If it's an attack already unfolding, you don't want to, you want it to know as soon as you can. And this is why online prediction becomes very critical. So we wanted to push the boundaries for our Dataflow pipeline a little bit more. It's like, hey, within our fixed window, all the data that we're receiving and we're extracting, can we have a branch out of it to predict at the same time, right? So in this way, we know right away for our latest information or the data that we're receiving, is there an anomaly or not? So how we are actually going to do that? So let's look at this. So I put together a diagram here, and it kind of explains, I feel like it kind of explains what you're trying to do. So remember, for k-means clustering, so it's going to group your data to a bunch of, or at least 4 different clusters based on the model that we have. Now, we also normalize it, right? So we know that, hey, what is within our cluster, what are the normalized distance for the points, right? So all those input vectors that's coming in, we wanted to be able to know. So the 2 things, we wanted to be able to know how close or what is the nearest centroid for those input vector. Now that we know the nearest centroid, how far, then we have to find out how far that point from our standard deviation. So for example, if it's going to be an anomaly, so if you look at another circle around our cluster, so it's going, if you look at one cluster, standard deviation is the inner circle, but we could also look at the 3 cluster standard or 2 cluster standard deviation is the outer circle. But if our input vector is outside that circle, we could probably safely assume that, hey, this is an outlier or this is an anomaly, right? So let's look into our Dataflow pipeline. So what we did here, oops, okay, so here. So what we did here is, as a side input, so remember the normalized table that we created, we're trying to feed into that table just by querying BigQuery. So if you look at that, we're reading from BigQuery, and we are creating a side input as a centroid vector. So now that we have that vector, it allows us to create an anomaly detection transform. So all those information or all the data, that extracted data we're receiving, we're creating a branch out of it, and we're passing it to our anomaly detection transformation. And there are only 2 things we're doing within that transform. We're trying to find out, hey, give us the nearest centroid. And then now that we know the nearest centroid, how far we are from the nearest centroid, right? So if those 2 transformation, when all the data, it goes through those transformation, And then if anything found, so if anything that's a 3 standard deviation above the mean, we know that this is an outlier. And on that time, we don't want to cause any delay. We want it to stream out to our outlier table in BigQuery, which is where is this transform here. You could see that if you remember when you started the demo, we published a couple of outliers. I think there are 2, and I have one for my GCS bucket. So the total number becomes 3 here. So let's go and query our BigQuery table, which is the outlier table that we have, which is this one here. And you could see there's a lot of demos. I have a query saved. I'm just going to query this. Let's do outlier join. Okay, so, and I'm going to make it a little bit bigger. So if you look what we're doing here, we're trying to join our outlier table with another table which we're calling a wireless subscriber data. And the reason we're doing it, even though we know the subscriber ID, we may not be able to know the full details of that subscriber, which is email and phone number, right? So let's run it. Now, remember for the DLP transformation, all those data is actually tokenized. And based on the tokenized, the token that generated by our DLP API, we're trying to join with our, our customer table, which is wireless subscriber data. So what it shows is, even though the data is tokenized, you could use that token to join other table, as long as you're using the same template, same DLP template to do the transformation. Okay. Now, if you look at this, so this is our subscriber ID, and it also shows email and phone number because we're querying the wireless subscriber table. But this data is actually no use, right? So because there's no way you would know what the subscriber ID is, what the email was, or actually what the phone number. So what we do is, so there is a re-identification pipeline. So we could literally fill in this query to a Dataflow pipeline, which is a different Dataflow pipeline. And I'm just going to run it very quickly. Just wanted to make sure that this is the right data. It's actually here. So let's run it. So what it's going to do is it's going to execute that query, and it's going to re-identify this data based on the template, right? So while this thing executes, let me just walk you through what we have done so far. So we started with publishing some PubSub data, publishing some mock data in our PubSub topic. We also put some, some random data for our cloud storage bucket. We have our anomaly detection pipeline, reading data from both sources, extracting it or extracting the features in real time with a very short window. We're passing those data information to our cloud DLP APIs for de-identification transform. A lot of those feature, or at least all the feature extracted data, we're doing a batch insert to a partition table in BigQuery. And we're also feeding those data within that window to our outlier transformation for the online prediction. So when this thing completes, we're streaming those data back to an outlier table where we are joining based on the MSI token or the de-identification token to one of our base customer table. And now we are running the re-identification pipeline to see that, hey, what is actually the actual subscriber ID? Wanted to be able to see that, hey, is it actually the right information? So it looks like it is completed. So let me just quickly do a PubSub, actually do a clear first. And I'm going to pull this information from, so this re-identification pipeline is also open sourced, and it's going to read from BigQuery based on the query that I just showed you, and then publish it to a PubSub topic. Now at this time data is re-identified, so not it's the original text data. So you could actually, you'll have to make sure that you have proper access control in place for that PubSub topic or the subscriber. So you could see that when I pull it, it actually correctly identified. So if you remember the subscriber ID, that was the subscriber ID that we published. and it also re-identify the phone number and email. Now those are all mock data, but I just wanted to show that that hey, this is the correct information. So that concludes our demo. So there's quite a bit going on in here. One thing I just wanted to say though, so a lot of our customers, they use the signature-based detection to predict cybersecurity threats. Given the lots of data, the IoT devices and the 5Gs, it may not be enough, right? Because there's so many different risks, new risks coming in every day. So you have to think about how you could use machine learning, and what you just have seen is how easy it is to put together a end-to-end reference architecture or an implementation using so many different Google Cloud technologies. Everything that you have seen here, it is open sourced. So all you have to do, just go to Google Cloud Platform. I think you could just search by DLP or Dataflow. So this is the one that contains our anomaly detection pipeline. This is where the re-identification pipeline is. And for one of those wireless, the main subscriber table that we de-identified, for a lot of the subscriber information actually belongs to this repo here. So that's pretty much it. I hope you enjoy this demo, and thanks for watching.